Hello, Physics 2B students. Welcome to Week 5B, our second lecture of Week 5. As promised, today we have a coverage of weird resistor circuits. Resistor circuits that don't fit into the mold of series and parallel. And that's what our warm-up is going to be on today. So the warm-up will be on a circuit similar to this one. So the majority of the class today I'm going to be doing coverage of this circuit as an example, and then I will make up a secondary circuit and walk you through that one as well. The warm-up is a combination of multiple choice and numerical, so you should be able to work through it. It includes not just getting to the answer, but actually the process of getting to the answer, so it's a mixed bag. It's 10 questions, and 10 points. The very last point is actually for coverage of an RC circuit. And exactly what I want covered for that, I will be covering that at the end of this lecture. All right. For the discussion, I want you to get practicing on these resistor circuits because next week there's going to be a video covering the practice exam that I am making available for you this weekend. And also, I want to make sure that you guys are ready for the first big exam next week, Thursday, for your class, for section 7. So without further ado, let's cover this last bit of material. These few slides, and then we'll be there. So none of these resistors are in series with each other. And we can see that when we draw a line. Because when we get to this segment B, junction B, there's a junction, therefore that breaks series. Next, going the other way, we get to a junction that breaks series. Okay. In that way, each one of them seems to be on their own line. So each of these resistors are segmented by junction B and junction C. Therefore, none of them are in series. Also, none of them are in parallel. None of them are in parallel because although 4 and 2 share this node with each other, they do not share the other one because a battery is in the way. And then 6 and 2 share this node, but they do not share the other because the battery's in the way. So nothing's in series, nothing's in parallel. What can we do for a weird resistor circuit? We still have the Kirchhoff laws, and we still have Ohm's law. So what we're going to do is we're going to break this down using specifically the Kirchhoff laws. Ohm's law is going to be sprinkled in there. And whenever we have a voltage across resistor, we're going to use IR instead of V. Okay. But before we get to the voltages, let's deal with the current. We have the currents pre-drawn in there. Current 2, current 1, and current 3, all relative to junction C. Okay. I'm going to use the idea of the junction rule not to show it's happening at C, but to show it's happening at F. At F, there's current going into F, and there's current going out of F. And because there's no other place for it to go, this must also be I2. Same thing on the other side of the battery. And the same thing going up resistor 4 ohms right there. In that way, we can say that there is our 4 ohm resistor has a current of I2 through it. The 6 ohm resistor, it's a little easier. It's just a continuity right there. So I1 goes through the 6 ohm resistor. And 3 goes around corner D and around corner A. And that is I3 in both cases. And there we have it. We now have the current noted at all locations. That's going to be really helpful in a moment. Let's go back to that first junction. We can use this first junction to identify what's going on with Kirchhoff's junction law. Specifically, Kirchhoff's junction law says that the current into a junction is equal to the current out of said junction. Our junction is junction C. 2 of those arrows are pointing into it. Specifically, I1 is pointing towards C, and I2 is pointing towards C. I1 plus I2. On the other hand, we have out. I3 is pointing away from I3, so from junction C, I mean. Therefore, it's like so. I'm going to rearrange this equation so that it's useful for some purposes we're going to have later on. Specifically, I'm going to rewrite this so that it's 0 is equal to I1 plus I2 minus I3. And every single one of those, I'm going to put a 1 in front of them. Because you can always multiply by 1. 1 I1 plus 1 I2 minus 1 I3. That's our first equation. And it comes from Kirchhoff's junction law. Equation 2. For equation 2, I need more information. The more information that I need is I need to know about the voltage across these different resistors. I already have a statement of there being a high voltage on this side of the battery and a low voltage on this side. I also know that there's a low voltage on this side and a high voltage on that side. And that thing I just said about the 14, that should have bothered you a little. That's a weird result. That is not the way that current normally flows. So what do? We're going to make a note of it. We're going to say normally current flows out of the positive side of a battery and into the negative side of a battery. This seems backwards. Therefore, hence the word backwards, I am expecting I2 to be negative. Because it just doesn't seem right. Okay. So I'm going to keep on going with this. I'm going to say the book I got this from says that the current 2 is labeled in that direction. So I'm going to go with it. It's different for the resistors though. When it comes to resistors, we're dealing with an electric field pushing that current through. And electric fields are always in the same direction as the current. And electric fields always point from the high voltage to the low voltage. So for my resistor, this is the high voltage side, this is the low voltage side. And I'm going to do this for every single resistor. Where the current goes in to the resistor, that's the positive side. And where it points out of the resistor, that's the negative side. Okay, the 6. It goes in on the left, that's the positive side. It goes out on the right, that's the negative side. Here, it goes in on the right, that's the positive side. And it goes out on the left, that's the negative side. Okay. I do not need to worry about voltage differences for the wires, because the wires have no resistance or negligible resistance. Therefore, the voltage across them is going to be 0, because voltage is equal to current multiplied by resistance. No resistance, no voltage drop due to any sort of resistance. But current still flows through there. Now that we have all of our highs and lows labeled, we can work on Kirchhoff's loop law. And I'm going to start with the top loop. Kirchhoff's loop law says if I add all of the voltages together in a loop, start at one point, go around, by the time I get to the end, back where I started, that should add up to 0 volts total. So 0 is going to be equal to, firstly, we're going from the high side to the low side of the voltage across the 4 ohm resistor. So that will be a decrease. More so, it's a decrease in 4 ohms multiplied by I2. And we get that from Ohm's law. Next, we're going from the high side of the battery to the low side of the battery. That's a decrease. And that's a decrease of 14 volts. Keep on going around. No voltage drop across the wire. And we continue on all the way to I1 and 6, where we have a low side to a high side. That's going to be an increase in voltage. Using Ohm's law, that voltage is 6 ohms multiplied by I1. And lastly, we're going across the battery from the high side to the low side, which is a drop of 10 volts. Both voltages are negative in this case, negative 14, negative 10. So those will combine to be negative 24 volts. And when I move them to the other side of the equation, they become positive 24 volts is equal to negative 4I2 plus 6I1. I'm going to take this result and I'm going to bring it all the way over to my listing area. 24 is equal to, what's the I1 term? The I1 term is positive 6. I1. I2 is negative 4 I2. And it has no I3 term. So 0 I3. Next loop. For my next loop, I'm going to use orange. I'm going to start at A, and then I'm going to go around like so, in this order. Don't need to worry about the wire. First voltage. We're going from the negative side to the positive side of this thing. That's an increase in voltage of 10 volts. Hope you didn't mind that rustle in the background. That was just the dog settling in. He thinks I'm recording this video too late at night, but I think we're going to be okay. Keep on going. Next, we're going from the high side to the low side. That's a drop in voltage. And it's a drop in voltage of 6 ohms multiplied by I1. I'm going to keep on going around. And we get to the high side to the low side. That's a drop in voltage. Then specifically a drop in voltage of 2 ohms multiplied by I3. And that brings us all the way back to A. All done. Let's rewrite this. I'm going to write it so I have the 10 volts on one side and all the other negative stuff on the other side. That's going to be 10 is equal to positive 6I1 and positive 2I3. I'm going to take that and put it with my other two equations. 10 is equal to 6I1. There's no I2 term, and positive 2I3. That's the equations we have. That is 3 equations and 3 unknowns. That combination, I many times call it inequations and unknowns. That means that there's enough information there to find out what I1, I2, and I3 are. Before I do that, I'm going to make a note of one more loop we could have done. That one more loop we could have done is the outer loop. Starting at A, going all the way around this outer loop, and getting back to A. Because the beginning is always the end. For that loop, first we go across the wire, that doesn't count. Then we get to the 4 ohm resistor. That's going to be the 4 ohm resistor multiplied by I2. We're going from the positive side to the negative side. That is a negative in front of it. Next, we then go across the battery from the positive side to the negative side. That's a decrease in 14 volts. We keep on going around, wire, 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 and our last resistor. from the high side to the low side. High side, low side. It's a decrease in voltage of twice I3. I can rewrite this equation to be 14. Yeah. 14 is equal to negative 4I2 minus 2I3. And I'm going to write that underneath the other ones. 14 is equal to, there's no I1 term. We've got a negative 4I2 and negative 2I3. That looks really similar to the blue and the orange equations. Okay. In fact, I get this exact equation if I take the blue equation and subtract the orange equation. 24 minus 10 is 14. 6 minus 6 is 0. Negative 4 minus 0 is still negative 4. And 0 minus 2 is negative 2. Okay. This is technically called a degenerate equation. Okay. Another way of saying it is it's redundant. Because all the information for this black equation is already in these two equations up here. So it's not going to be helpful for our calculations. Okay. So I'm going to erase that negative sign. And I'm just going to hold on to this for double checking later. Okay. So I'm going to put a double check next to it because that's what it's going to be good for. If everything goes right, that equation will hold true. Using the purple, blue, and orange equations, I'm going to solve this. 3 equations, 3 unknowns. I'm going to start by getting rid of I3. From this top equation, we can see that I3 is equal to I1 plus I2. So anytime I see an I3, I'm going to replace it with I1 and I2. The only other place I see it is here. Okay. So that my blue equation is still the same. 24 is equal to 6I1 minus 4I2. And I don't even have to mention I3. But the orange equation becomes 10 is equal to 6I1 plus 0I2, I'm not going to write that down, plus twice I3, which is I1 plus I2. Separating out those terms, I get 10 is equal to 6I1 plus 2I1 plus 2I2. Combining like terms gives me 10 is equal to 8I1 plus 2I2. Now I have this equation here and this equation here. 2 equations, 2 unknowns. Let's see if I can simplify this. I'm going to simplify both of these equations. Okay. I'm going to divide the top one by 2, firstly. Okay. So that this becomes 12 is equal to, so dividing it by 2, the whole thing. 12 is equal to 3i1 minus 2i2. That looks very similar to the other equation. 10 is equal to 8i1 plus 2i2. To the point where if I add them together, much like I did with the black equation earlier, something's going to cancel out. These two terms add to 0. 12 and the 10 add to 22. 8 and the 3 add to 11, I1. And when I divide both sides by 11, I get I1 is equal to 2.0 amps. That is one equation and one unknown solved. Let's keep it going. We've got one unknown turned into a known. Let's make the next one. I'm going to take that 2 and I'm going to plug it into this blue equation. When I do that, I get 12 is equal to 3 times 2 amps for I1 minus 2I2. I can move the good. Yeah, that looks good. I'm going to move the simplify first, then I'll move things around. 12 is equal to 6 minus 2I2. Subtract 6 from both sides, and I get 6 is equal to negative 2I2. Finally, I get that I2 is equal to negative 3.0 amps. You might be looking at this and going, wait a minute, why are we getting a negative current here? What does that mean? This was actually expected. Normally I, as in the current, flows out of the positive battery and into the negative side of the battery. This seems backwards, and by this I mean this looked backwards. Therefore, I'm expecting I2 to be negative. And it was. Lastly, let's check out I3. From our purple equation, I3 is equal to I1 plus I2. I1 is equal to 2 amps. I2 is equal to negative 3 amps. And I get that I3 is equal to negative 1.0 amps. This one's negative 2. That means that there were multiple things wrong with it, not just the ones that were evident in the first place. There was a second issue with the way that the arrows were drawn in the first place. This is a fair amount of algebra. It's a fair amount of algebra, and I've done this just today. I've done this one problem 4 times. And one of those times I made an algebra mistake. And this is a problem I know. So in these problems, it's really easy to fall into algebra mistakes. So let's double check this. We have our double check equation up here in black. When I add my stuff together, I'm expecting 14. 0 times I1 is going to be 0. minus 4 times I2. I2 is negative 3. Minus 2 times I3. I3 is negative 1. That gives me, I'm going to not even write the 0. Negative 4 times negative 3 is positive 12. And negative 2 times negative 1 is positive 2, which gives me 14, which is exactly as I expected. Good and good. But it's still a lot of algebra to do. Do we have another way that we could check these things? Yes, we do. We can check these things using graphing calculators. Okay. Specifically, if you have a TI calculator, I'm going to copy and paste my equations over to here. And I'm going to go through the process for how you can solve this entire thing on a graphing calculator so you don't get lost doing algebra. This whole thing can be rewritten in a matrix format. The matrix format has all this stuff about the batteries first. So that's V vector is equal to, so it's the voltages, it's an array of voltages, 0, 24, 24, 10. Next, all of these numbers in here, not the currents, all the numbers. I'm going to call that my resistor matrix. And it's going to be 1, 1, negative 1, 6, negative 4, 0, and 6, 0, positive 2. That's my resistor matrix. How the currents get in there is that voltage is equal to that resistor matrix multiplied by the current vector. But I can get rid of this. I can solve this for the current by multiplying both things by the inverse of R, specifically on the left-hand side. Okay? It has to specifically be on the left-hand side so that these two are next to each other and they cancel out. That gives me that the inverse of the resistor matrix multiplied by our voltage array is going to be equal to all of our currents. We could put that equation into the calculator by first plugging in all of those values into one matrix, plugging in all of these values into a second matrix, and applying that equation. On my calculator, I'm going to press second matrix. Both of those are on the upper left-hand side. Second's usually yellow, and matrix is 3 buttons below that. When I do, I get a list of options, names, math, edit, and I'm going to move the cursor over to edit. And I'm going to select matrix A. Matrix A is going to be my resistor matrix. Okay. Matrix A, also known as our resistor matrix, is a 3 by 3 matrix. and it has values of 1, 1, negative 1 in the first row, 6, negative 4, 0 in the second row, and 6, 0, 2 in the third row. I type all those in really quickly. 1, 1, negative 1, 6, negative 4, 0, 6, 0, positive 2. And then I'm going to quit out. Second quit. Now I'm going to press second matrix again. And when I do that, it gives me that table again, and I'm going to go to edit. And we're going to edit our second matrix, labeled B. B is going to be our voltage matrix. For matrix B, it is a 3 by 1 matrix with values of 0, 24, and 10. Entering those in, 0, 24, and 10. Then I quit out of that screen. Next, so I created both of these matrices. Now I need to type out my equation. I need to type out the R inverse first. Remember that R is matrix A. So that's going to be second matrix again. And I'm not editing anything this time. I'm just going to enter A. And then A will appear on the screen. Now I need to add the inverse. That inverse button on my calculator is the same as the matrix button. So you have your matrix, put the inverse in there too. Next, second matrix one last time. And we're going to put the B matrix in there. So now it reads out A inverse multiplied by B on the screen. And I press enter. And I get 3 numbers written on the screen. 2, -3, and -1. Those are our 3 currents. Current 1 is 2 amps. Current 2 is equal to -3 amps. And current 3 is equal to -1 amps. Exactly what was calculated over here. 2, -3, -1. Done. That's our technique. What do you need to be able to do during an exam? Okay. Well, I'm going to try to minimize the math you have to do on the exam. Okay. So, what I really want you to be able to do is break down the circuit. That's where the physics is, because it's a physics class first, but we use a lot of math in the physics class. And then we mostly need to be able to break down that circuit. So a problem that always appears on the midterm for me is me giving you a circuit and saying, all right, from that circuit, I give you a list of a whole bunch of equations. Which of these follow the Kirchhoff laws for this circuit? Okay. Mixed into there would be these 4 equations and a couple others that are similar, or what might happen if you get a negative sign wrong. Okay. Because it's surprising how big of a difference a single negative sign can make. Okay. So be very careful about that. There will be some calculations you have to do, but I try to avoid the Mondo calculations like this. Okay, that's a math assignment, not a physics assignment. But there's the process. There's the process where you can do it by hand or by calculator. Either way. So let's see what this looks like for a different circuit. Our different circuit is going to have a battery like so. That is going to be 15 volts. A resistor like this, that's going to be 10 ohms. A resistor like this, that is going to be 20 ohms. A resistor here, actually I'm going to put it around the end. Battery first. This battery is going to be 13 volts. And a resistor that is 30 ohms. What do I need to do here? Well, I need to identify highs and lows. Looking at the batteries always have a high side on the big side and a low voltage side on the small side. High voltage side on one side, low voltage side on the other. And that is what's going to push our current. The current points out of the positive side. So this is going to be the current through our 10 ohm resistor. I'm going to call that resistor 1. So that is going to be current 1. The 13 volt battery is going to have current pointing out of it like so. That's the same current that is going through the 30 ohm resistor, which I'm going to call R3. As such, that is going to be I3 pointing through. So I got those 2 directions from the battery. What's going to be the direction through the 20 ohm resistor? Well, I've got 2 currents going into that junction. And when that current goes into that junction, it's not just going to cancel out. It's going to keep on going. So they're going to combine. And when they combine, they get pushed out this way. That's the direction of I2, which is across resistor 2, the 20 ohm resistor. We now have the direction of the current across all 3 resistors. And we can use that to determine the high sides and the low sides for each resistor. Remember that for resistors, the current goes in the high voltage side and out the low voltage side. In the high voltage side, said it correctly that time, out the low voltage side, in the high voltage side, out the low voltage side. There we have it. Positives and negatives have been identified. Now let's set up our junction rule. Junction rule looks pretty set up for me already, because I've already got everything identified having to do with this purple dot at the top. So at that purple dot, I'll have current in is equal to current out. The current into the junction, that was 1 and 3 pointing into it. And current 2 pointing out of it, which can be rewritten as 0 is equal to 1I1 minus 1I2 plus 1I3. Just a rewriting of that same equation. Next, loop on the left. Loop on the left, I'm going to start there and measure all the way around to the original spot again. In this loop, it all adds to 0. That's the loop law for you. First across the 15 volt battery, low to high, that's an increase of 15 volts. Next element, high to low, that's a decrease in voltage of R1, which is 10 ohms, multiplied by I1. And then high side to low side, that's a decrease in voltage of 20 multiplied by I2. This can be rearranged to be 15 volts is equal to 10I1 plus 20 I2, which I'm going to rewrite underneath the purple as 15 volts is equal to 10I1 plus 20I2, and then there's no I3 in there, so 0 I3. Next loop. This next loop I'm going to do in green. I'm going to start here. I'm going to measure around this thing. Like so. And because this is a loop law, it always adds to 0. 0 is equal to, from the negative side to the positive side, that's an increase in voltage of 20 ohms multiplied by I2. Continuing around, wire, 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 battery. From the positive side to the negative side, that's a negative voltage of 13 volts. Keeping it going. Negative side to positive side, that's an increase in voltage of 30 multiplied by I3. I can rewrite this as 13 is equal to 20I2 plus 30I3. Or, for my equation down below, 13 is equal to 0I1 plus 20I2 plus 30I3. Let's do that double check equation too. That double check equation, I'm going to start the bottom left hand corner. It doesn't matter where you start, I'm just trying to be consistent. Okay. What matters is that wherever you start has to be the same spot as where you finish. Closed loop. This closed loop, the voltages need to add to 0. We're going across the 15 volt first, low to high, plus 15 volts. Next, the resistor 1, positive to negative. That's negative 10I1. Next, keep on going around. 13 volt battery, but we're going from the high to the low. That's a decrease in voltage of 13 volts. And then our last element, resistor 3, negative side to positive side. That's going to be an increase of 30 multiplied by I3. When I combine these, I end up with twice the voltage, so 2 volts, is equal to 10I1 minus 30I3. And it's just 1 or 2 steps of algebra from one to the other. I'm going to rewrite that equation underneath the green one, and I get 2 is equal to 10I1. There is no I2 in there, and negative 30I3. Does this make sense? Did I make any mistakes? Well, let's check it out. If I subtract the green one from the blue one, I get 15 minus 30 is 2. Good. 10 minus 0 is 10. Good. 20 minus 20 is 0. And 0 minus 30 is negative 30. Everything checks out. No mistakes so far. Those are our 4 valid Kirchhoff law equations for this circuit. What's the result? I'm not going to do the algebra again. Instead, I'm going to use my calculator. And in the calculator, I'm going to have the voltage matrix be 0, 15, 13. And the resistor matrix is going to be 1, negative 1, 1, 10, 20, 0, and 0, 20, 30. To the calculator, second matrix, editing the first one, that'll be 1, negative 1, 1, 10, 20, 0, and 0, 20, 30. Now, to edit the second matrix, 3 by 1, that it says 0, 15, 13. When I put all this into my calculator, the result I get is current is equal to 0.445. Then the 4 5s repeat over and over and over. That's I1. I2 is equal to 0.527. And then the 2 7s repeat over and over and over. Then I3 is equal to 0.081. And the 8 1s repeat over and over and over again. That happens a lot in the circuits I randomly create. Let's double check that this result makes sense. Okay. So I'm going to put these values into here, and it should all add up to equal 2. So that'll be 10 times I1 of 0.445 plus, I'm skipping 0 I2, and doing minus 30 multiplied by 0.081. What do I get? 10 times 0.445 minus 30 times 0.081. And I get 2.02. Are they equal? Not exactly. Are they good enough? Yes. They're good enough because I know that there's some rounding issues because this is a repeating decimal. All of these have repeating decimals in there. So this rounding here is okay. So what I'm going to suggest is you try this circuit at home. Okay? Set it up again with our 15, 10, 13, 30, and 20. See if you can set it up and get these same equations. And then try the algebra out. Can you get through the algebra through a series of substitutions and end up with these three currents? Give it a try. That'll be something that you can practice over the weekend. If you can do all of that, and you can also do the warm-up for today, you're going to be in good shape for these complicated circuit sections. But we got one more complicated circuit. Our one more complicated circuit is an RC circuit. We got a change of gears happening. Okay, so take a quick breath. In an RC circuit, we're going to have two different forms. The first one involves a capacitor and a resistor and a switch. The capacitor starts fully charged. When you close the switch, current starts flowing out of the capacitor, which discharges the capacitor, and we end up with current flowing through the resistor. The one issue is the more current flows out of the capacitor, the weaker the current. So we end up with this exponential decay. This exponential decay shows how the current is decreasing with time, not linearly, but as an exponential approach to zero. And the weaker the charges, the weaker the resultant current is going to be. So the current, as a function of time, is going to start with some initial current, and it's also going to exponentially decay, like so. I'm expecting the same shape for both of these graphs. I'm expecting the same shape because of Ohm's law and because of the voltage for the capacitor equation, but most importantly, due to Kirchhoff's loop law. That says the voltage across the capacitor and the resistor must be the same when they're the only two elements in our loop. So that the charge divided by the capacitance is the same as the current multiplied by the resistance. As the charge gets less and less, the current gets less and less. And that's what we see here. Going to keep it to that concept, and we're going to skip the calculus. Let's look at this again. But in this again, we're going to be looking at a different version of the circuit. instead of a discharging capacitor, we're going to look at a charging capacitor. How is this capacitor being charged? Well, the capacitor is starting at 0 volts and 0 charge. It's getting charged, though, by the battery, but not until the switch closes. Okay. So the charge in the capacitor is going to be increasing, and it's going to be kind of a flip of what we had above there. The charge, as a function of time, is going to exponentially approach some maximum value. And that maximum value that it is exponentially approaching towards is Qmax. I want to analyze this circuit at 3 important times. Time 1, when the switch closes. Time 2, when the whole thing is half charged. That's Qmax divided by 2. I'm going to call that time T1 half. And lastly, at some big time later, when the charge is effectively Qmax after a very long amount of time. At those 3 times, I want to know everything about the circuit, though. Okay, so there's the property, and then there's the times. There's t is equal to 0 when the switch closes. There's going to be T1 half charged. And T big, which is fully charged time. What do we want to know for each of those times? We want to know the voltage across the battery, also called the EMF. We want to know the voltage across the capacitor, which is also equal to VC is equal to charge divided by capacitance. Very helpful information. We want the voltage across the resistor. Remember that the voltage across the resistor is equal to current multiplied by resistance. And to help us through there, it's going to be very helpful to know the charge at each of those times and the current at each of those times. There we go. Full table. One of these columns is easy to fill out. And it's easy to fill out because it doesn't change. And that will be the voltage across the battery. We're using a DC power supply, which means that it's providing a constant voltage. That constant voltage is going to have a value equal to the EMF. So whatever the EMF is, it's the same at all 3 of those times. Next, looking at the graph, the charge is 0 at one of those times. It's 0 when the switch just closes. Just as the switch closes, the charge is 0. Nothing's accumulated yet. And since the charge is 0 at that time, then the voltage is going to be 0 as well. The voltage is going to be 0 as well because if the charge is 0 and it is a capacitor, then the voltage across that capacitor is 0. That leaves the resistance. And in our loop, the two sides of this equation have to be equal. If the capacitor voltage is 0, then all we're left with is that the EMF is equal to the resistor voltage. Which is the EMF. Since that's our voltage for the resistor, that means the current will be equal to the voltage across the resistor divided by the resistance, which is going to be the EMF divided by the resistance. 1 time done, 2 to go. Fully charged. Fully charged is actually an easier one, but it's only easy if you know very specific concept. Remember that there's a relationship between the charge and the current. At this point in time here, in green, the charge is constant. The charge is not changing. dq, or delta q over delta t, is equal to 0. It's not changing. Also remember that delta q over delta t is the same as the current, by definition. Therefore, the current at time big is equal to 0. The current at time big is equal to 0. I can use that information for my resistor. If there's no current, there's no voltage across the resistor. Boom. Which leaves us with only one other thing that voltage can be across. That's the capacitor. So if you've got a voltage of the EMF being applied, then that's also going to be the voltage across the capacitor at that time. And to calculate the charge is equal to the voltage multiplied by the capacitance. That's going to be the EMF multiplied by whatever the capacitance is. Last row. For our last row, we already know what the charge is, because I said it. It's half charged, and we already know what the fully charged is. So I'm going to take my fully charged and divide that by 2. Electromotive force multiplied by the capacitance divided by 2. I can use that charge to get the voltage across the capacitor by taking that charge and dividing it by the capacitance, giving me the EMF divided by 2. Which means that in our loop, the capacitor is only using up half of the voltage, which means that the resistor needs to use up the other half at that time. And since the voltage is at half for the resistor, then the current is also going to be at half for the resistor. Okay. I want you to be able to identify when the currents are 0, when the voltages are 0, when the charges are 0. So just see the pattern of charging and discharging for these in terms of these quantities. Watch this a couple more times. See if you can get the pattern without hearing me say it. And hopefully you'll be good at that point. It's also covered in the book with different words and with a little bit more math. If that helps you understand the concepts, that's good. But this is all that I'm looking for you to understand for RC circuits. Okay. So to summarize for today, practice as many circuits that have multiple batteries and multiple resistors as you can. There's a whole bunch of options in the book. Okay, so do feel comfortable going through the book. There's a whole, if you look at the end of the chapter, it has circuit after circuit after circuit available. The 3 steps. The breakdown of the circuit is the most important part. Being able to take a circuit, identify the increases and decreases in voltage, and creating the equations for them, that's key. That's the physics. That's the part that will absolutely be worth a few points on the exam. Solving it, be a point or two based off of that, but not as much. Okay? Because my emphasis is more so on what do you have going on with the physics, less so the math. If you have a TI calculator, a TI graphing calculator, excellent. That means that you'll be able to double check the math, and the warm up tonight will be easier for that reason. If you don't, then you got some algebra to practice. And once you're done with it, double check that your results are true. Go to your double check equation and actually make sure that that one holds true too. Okay. That's it. That's the end of Unit 1. Happy studying. Email me if you have any questions. I've already gotten a few emails tonight, so I'll be answering more as they come in. That's it. Next week we'll be doing the practice exam, which I'll be making available to you over the weekend. And then we will be having just the exam on Thursday, if you're in Section 7. And if you're someone in Section 1 or 6 watching this, the exam is on Wednesday morning. That's it. Good luck with your studying. I'll talk to you more soon.